Have you ever stopped to think about how your computer decides what to do next? It's juggling a million things at once, managing tasks, sorting your files, handling all that network traffic. There's this constant invisible prioritization happening behind the scenes. So, how does it always know what's the most important thing to tackle right now?
Well, let's think about it like this. How does a computer handle a waiting line? That's a question it has to answer like millions of times every single second. But here's the catch. This isn't your typical, first come, first served kind of line. We're talking about a queue where importance can change in a flash.
Okay, picture this, a customer support system. You've got hundreds of people waiting. So who gets the next available agent? Is it the person who's been patiently waiting the longest? Or what about that VIP customer who just jumped in the queue? See, this is exactly the kind of problem computers have to solve all the time. And that right there, that's the core challenge we're talking about. We call it the priority problem. If you just have a simple everyday list, finding the most important thing means you have to look through the entire list every single time. And as that list gets bigger and bigger, forget about it. It just gets way too slow. There's got to be a better way, right? And of course, there is. The solution to this whole priority mess is a really, really clever data structure called the heap. So what in the world is a heap? Well, at its core, it's a special kind of binary tree. Where everything has at most two children. But this tree has one single-minded mission in life: to make sure the item with the highest or lowest priority is always, and I mean always, sitting right at the very top. It's ready for you to grab instantly, no searching needed. And how does it pull this off? It all comes down to one simple rule, something we call the heap property. And it comes in two flavors. You've got your max heap, where every parent is always bigger than its kids, and then you have the min heap, where every parent is always smaller. That's it. Seriously, that one rule, that's the key to the whole thing. Okay, check this out. You can see that rule in action right here. This is a classic max heap. See how the biggest number, 98, is sitting right at the top? And look, if you pick any parent, say 50, yep, it's bigger than both its children, 49 and 47. That rule holds true all the way down the tree. Here's a really great way to get your head around this. Think of a max heap like a company's org chart. The most important person, the CEO, is always at the very top. Now, it doesn't say that a manager in one department is more important than a manager in another, but what it does guarantee is that the boss is always on top. So it's super important to understand what a heap is not. You might be thinking of other tree-like things, maybe a binary search tree, right? Those are all about fast searching. But a heap? Its job is totally different. A BST is built for searching through everything. A heap is built for one thing and one thing only, getting you the biggest or smallest item, like right now. It's a total specialist. Okay, so that all sounds great when everything's just sitting there. But what happens when you add something new or take something out of this perfectly organized structure? Well, that's where the real magic comes in, the reshuffling. All right, let's start with adding a new value. The process is actually pretty simple and makes a lot of sense. First, you just stick the new item in the next open spot at the very bottom. Now, this might break our big rule, right? So you compare it to its parent. If the new guy is bigger, you swap them. And you just keep doing that, letting the new value kind of bubble its way up the tree. We call it percolating up until it lands in the right spot. Let's actually see this in action. So here, we're going to insert the number 85. It gets plunked down in the next open spot, and now it's a child of 80. But wait a second. This is a max heap, and 85 is bigger than its parent, 80. Uh-oh, that's a direct violation of our one big rule. But no worries, the fix is totally automatic. The heap just swaps 85 with 80, and boom, the rule is restored. It's like that new value just bubbled up to exactly where it was meant to be. Okay, so that's adding. What about when you want to remove the most important item? Well, that's always the one at the very top, the root. So to fill that empty spot, you do something kind of weird. You take the very last item in the whole tree and move it all the way to the top. Now, this is almost guaranteed to break the rule. So you compare this new root with its children, swap it with whichever one is bigger, and you just keep repeating this, letting it sink down the tree. We call this percolating down, until the order is fixed. Visually, here's what's going on. First, we take out the highest priority item, 88, gone. Then, the last element in the tree, which is 80, gets yanked up to become the new root. And right away, we have a problem. The new root, 80, is smaller than one of its kids, 85. The heap is, for a moment, totally broken.
And then, just like magic, the heap fixes itself. It looks at 80, compares it to its children, sees that 85 is the bigger one, and performs a swap. The value sinks down, and once again, our heap is perfectly ordered and follows the rule. It's pretty cool, right? It's like a self-healing data structure. Okay, this all seems incredibly efficient, right? But the real key to why a heap is so fast, its cleverest little secret, isn't actually the tree shape we've been looking at. Nope, it's how that tree is secretly stored.
So what is it? What makes heaps so unbelievably fast and efficient? I mean, why is this structure so much better at this priority game than just a regular old list?
Okay, and here's the big reveal. Even though we draw a heap like a tree to make sense of it, inside the computer's memory, it's actually just a simple, flat array. That's it. There are no complicated pointers or nodes connecting everything. It's just a list of numbers, all lined up in a very, very specific order.
And this is where the real genius is. The computer can navigate this tree using nothing but super simple math. If you know an item's position, its index, in the array, you can instantly calculate where its parent is or where its children are using these simple formulas. That's why heaps are lightning fast. It's all just basic arithmetic, not slow and clunky memory chasing.
So this incredible efficiency leads us to one of the heap's most powerful uses. Turns out it's not just for managing priority queues. It's actually the backbone of a very famous and powerful sorting algorithm called, you guessed it, Heapsort. So the first thing you have to do is take any old random jumbled up list of numbers and rearrange it into a perfect max heap. This process has a great name. It's called heapify. And as you can see, it takes that messy list on the left and in one super efficient pass, it organizes everything so the biggest number, 98, is at the top, and our heap rule is followed everywhere. Now, once you've got that max heap, the sorting part is it's beautifully elegant. Think about it. The largest item is always right at the front, right? So you just swap it with the very last item in the list. Now it's in its final sorted position. Then you just pretend the heap is one item smaller. Fix the little mess you made at the top and repeat the whole process. It's a simple rhythm. Swap, shrink, fix. You just do that over and over until the entire list is perfectly sorted. When you get right down to it, the heap is kind of an unsung hero in computer science. It's this silent, self-healing organizer that's constantly working in the background, answering that one question we started with: what's most important right now? From the guts of your operating system to your network router, it's one of the big reasons our digital world feels so orderly and responsive. So the next time you see a progress bar ticking along or a list that's perfectly sorted, just stop and ask yourself, what else in my digital life is secretly being managed and prioritized by a heap?